3-phase full bridge inverter. So this is our first class in the live stream. So let us look at the switching pattern for this 3-phase full bridge inverter. As you know that inverter is a device which you will to convert, which is to convert DC supply to AC source. AC, which means that our input power supply is DC power, so it is the positive part, and here we have the negative part. The negative part here we have in between two, we have BDC here. So in that region we have some filtering mechanism here, which is a capacitor, in order to filter the supplying voltage in here in DC source. Then after, which is directly implement here the inverter part, which is so called the 3-phase full bridge inverter is in here. Full bridge inverter, this is the diode one, which is in order to protect the device from damage. Here again we have here another which is again another switch. Since which is a 3-phase, we need to have 3 in the up in the top leg, as well as in the bottom leg here. So here we have one IGBT insulated gate bipolar transistor. So here also insulated gate bipolar transistor. So let us assume that here, starting from here we have the input supply here, which is the input is DC. So this DC supply is just DC input is given to this inverter. This inverter, let's say this is T1 and D1. This is so-called T4 and D4. Here we have T3 and D3 here. Here we have D5 and T5. Here D2 and what? T2. So based on that kinematics, we need to have here our input is DC source, and that DC source is directly changed into AC supply here. Just let us take our power input from the first leg A, which is from A, and this is from B. This is A, this is B, and this is C. This is C, which is the power part, C. So here we have a 3-phase motor, so which is our output. So the DC voltage, which is maybe from series of batteries, or from somewhat another source so-called UPS, an interrupted power supply. So from that, the DC source is directly inverted into the AC supply electric motor. This is AC three-phase electric motor. So this AC three-phase electric motor need AC power, and this is a DC source. So the main thing we have to understand in this particular presentation is this inverter is a very important power converting or power switching mechanism in order to change the DC source into the AC source. So this is the general kinematics of the inverter. The next thing we have to remind or we have to recall in here is switching pattern. So to draw a switching pattern, we need to have to know about the the transistor or the so-called the inverter sequences. We have T1, we have T2, we have T3, we have here we have T1, T2, T3, again we have T4, T5, and T6. So this is switched on and off within a 60-degree delance of 180 with 180 degree and with 120 degree. So for the 180 degree conduction angle, we have a switching pattern, as well as for this we have another switching pattern, as well as for this we have a switching pattern. So first of all, in this particular case, let us draw the switching pattern for the 180 degree conduction. So for this case, let us draw the switching pattern here. So here we have, let's say here we have, this is T1, and here the second, this is T2, this is T3, this is T4, this is T5, this is T6. So now we have to separate the conduction angle within a 60-degree phase. Here each transistor sequence is differentiated from the other by a 60 degree. So let us here, this is a 60 degree, this is for 120 degree, this is 180 degree here, this is for 240 degree, this is for 300 degree, and this is for 360 degree. So our main target in here is just to draw the switching pattern in here. So the first thing, T1 is the first thing T1 is conducted in the 180 degree here. So this is a phi. No, this is not phi. This is a 60 degree. 60 degree. This is a 60 degree. This is 120 degree. This is 130 degree. So this is pi, and this is 2 pi. 2 pi. So in the first case, T1 is triggered. This T1 is triggered up to the 180 degree conduction. So this is our conduction period of T1. T1 will conduct up to 180 degree. This is 60, this is 120, this is 180. So this is the T1 conduction angle. So after 60 degree delance, the second T2 will conduct for 180 degree here. So this is conduction angle for the second T for T2. Again, this is for T3 here. This is for T3. This is for T3. Here 60. Here 120. Here is 180. Here 240. Here 300. 316. So the second T4 will conduct in this is T1, this is T2, this is for this case we need to have here for okay, so from here this is 60 degrees, this is 120 degrees, this is 180 degrees. For the second case, this is off and this is on. This is 60, this is 120, this is 180 degree. Again, this is off, 60 degree, 120 degree, and 380 degree. For this case, this is 60, 120, and come back here. Here, the switching pattern back to here. So in this, we have here I missed one pattern in here, so let us move to the next one. So let us move to the next one here. Okay, for 60 degree. Okay. 1, 2, 3. T6, T4 will conduct in here, T4 will conduct in here. So this one is for 120 degree. This T5 is conduct for here and again back to here. T6 here and back to this. So generally the switching pattern for this controlling mechanism is T1, T1, T5, and T4 first, second T1, T1, then T2, T2, the T4 here. No, T4 is not conducted at the same leg. T1, T2, and no. T6.